So in class we looked at how to find the gradient of a function that we had just as a line by just looking at how far along it goes and how far up it goes each time. Now that works quite well most of the time, but you'll notice that there are some functions, such as this one here that I've drawn, where if I go along one, then actually seeing how far I go up isn't such an easy task, because I'm not quite sure, I know it's kind of a fraction, but it's not really very clear to see. I can't do it very precisely. And in fact, if I go along one unit rather than just one square, it's also not very clear to see. So in this situation, we need to use a different trick. What you need to do is you need to just find 2 points on the function. So 2 points where it goes through a point that we recognize. So here's our first point. We know it goes through the point 0, 0. And if we look up along, then I can see that it also goes through this point, where x is 10 and y is 6. And we can use a thing called the difference quotient, I've given it to you in German here as well, to enable us to find the gradient of any graph. So this works for any graph. And the difference quotient is given by, if we take f of x2, take f of x1 divided by x2 minus x1. So in this case, x1 and x2 are just x points. So in this case, we have 1x here, let's get a different colour, at 0, and another one here at 10. So I can define which of these will be my x2 and which of them will be my x1. As I'm doing x2 minus x1, then it would be best if I did this is x2 and this is x1. And that's also convention, to have your x2 as the one that's further along. So I've got an x2 and I've got an x1. Now I need to find out what f of x2 is. So for the x2 value here, what is the value of the function at that point? Well, we know already that it's 6. So this one here, if I find this colour, let's circle it so it's clear, this 6 is just f of x2. And f of x1 is also quite easy to read off. It's just this 0 here. So I have my 4 numbers, and I can put them in to this difference quotient to find the gradient. And actually, you'll notice that this is really similar to what we've already been doing. Because if I draw a big triangle from this point to here, and from this point down, then you'll notice that f of x2 minus f of x1 is just this 6 minus 0. So that gives us the length of this side here. Let's put it in orange, it's a colour I haven't used yet. So we have here f of x2 minus f of x1. It gives us the length of this line, this side of the triangle, because I'm just doing 6 minus 0. And x2 minus x1 gives us the length of this line here, the length of the other side of the triangle. So in this case we have 10 minus 0. And so if I divide this by this, then it just gives me the gradient. And that's a useful thing for the difference quotient. We can find the gradient without drawing really big triangles or trying to figure out what kind of fraction this is when we go along one. So I just need to put my numbers into this formula here. So I had f of x2 was 6 minus f of x1 0 over x2 10 minus x1 0. So I've got 6 over 10, 6 take 0 is 6 and 10 take 0 is 10, and I can cancel this because I can recognise that 2 goes into 6 and 2 goes into 10. So 2 goes into 6 3 times, and 2 goes into 10 5 times, so my gradient is 3/5. So we can use this difference quotient to find the gradient of any graph. So let's write this down. We can find the gradient of any linear function using the difference quotient. And the difference quotient, as we had on our other page, will be equal to k, the gradient. So we have f of x2 minus f of x1 over x2 minus x1. It's a really fancy way of writing the gradient triangle that we have. So we can use this in exercises. I've taken 2 example exercises from the BFE, the people who write the final school leaving exams for Austria, so that you can see that this can be used in different ways as well. So this exercise here is a type 1 exercise, and we have this linear function here, f of x is equal to 4x minus 2. And our task, we need to choose 2 x values, x1 and x2, where x2 is 1 more than x1, and show that the difference between the 2 values when we put them into the function is exactly the same as the gradient of the given function. Now this should work because we know that our gradient is given by our difference quotient. And if x2 is 1 bigger than x1, then we have f of x2 minus f of x1, and I can substitute this x2 in here, like I might have done before with my simultaneous linear equations, and instead of x2 I can write x1 plus 1 minus x1. And then we see that here in the denominator I have x1 take away x1, so I'm just left with 1 in the denominator. So that actually should be equal to this, which is what the question asks. So that's why the question works, but to answer this question we don't actually have to go in that much detail. Let's choose an x1. I'm going to pick 0 because that will be much easier, and so my x2 will be 1. Then my f of x1 will be minus 2. 4 times 0 take 2 is minus 2, and f of x2 will be 4 times 1, which is 4, take 2, which is 2. So then my f of x1 and my f of x2 can now be put into this formula here. So I have f of x2 minus f of x1 will be equal to 2 minus minus 2 minus minus 2, which is 4, which is the gradient as we expected. You'll notice that in answering this question I was really careful to only put my equal signs in when I had equality. So now I can say that this is equal to k, because we know this from here, because we have kx plus d in the German form. This would be m in the English sense. But I was careful not to say that this was exactly equal to this before this point, or unless I proved it otherwise. So just be careful with your equal signs. So that was my first one I wanted to show you. The second one was this one. So we have the graph of a linear function with this equation. As I said before, don't forget that in English it would be mx plus c. And we know it goes through 2 points, P and Q. So this now should be really easy, because we can see that p is before q, it's at the point where x is minus 10, and q is at the point where x is 20. So actually, these values, we have p is minus 10, 20. I'll use the comma notation as I'm speaking in English. We know that then x1 is minus 10, and f of x1 is just this y value here, which would be 20. And for q, I have 20 and 5. So my x2, my second x value that I know, is 20. And I know that f of x2, so f of 20, is equal to 5. So all I need to do now, because my task here is to find the value of k, so I need to find the gradient. All I need to do is I need to put these numbers into the formula that I know for the difference quotient, and I can find the gradient. So I don't actually have to draw anything at all. If you were a bit stuck on this problem, if this came up in a test or in your examination, then I would recommend drawing the graph of the function, because that would be really helpful. But you don't have to. And if you don't need to, don't waste your time. So I know k is f of x2 take f of x1 divided by x2 take x1. So I can just put my numbers in. F of x2 is 5, take 20, divided by x2 minus x1. So I have 20 minus 10. Be careful with your signs here. So 5 minus 20 is minus 15 in the numerator, and 20 minus 10 is 20 plus 10, so I have 30 in the denominator. And this is something, again, that I can cancel. I know minus 15 goes into itself once, and minus 15 goes into 30 minus 2 times. So my answer cancels to minus a half. If you find it easier, you can have this negative symbol, the minus, out of the front here of the fraction. It doesn't matter which one of these it belongs to, as long as you only keep one minus so that you don't get confused. So we can show that the gradient here is minus a half, and we were able to do this exercise really quickly.